So hi everyone, welcome back to the afternoon session. And now we have Daniel ABREU telling us about local maxima of white noise spectrograms and interlacing of zeros in higher Landau levels.
Okay, so thank you very much for this wonderful conference and for the invitation. I'm going to try to be a bit pedagogic in some unusual points and short at most technical things. So the first thing and the most important thing that I want to communicate is the Landau levels operator. Okay? So the Landau levels is a physical model. It used to be the mainstream explanation for the integer quantum Hall effect before the advent of these topological theories. But somehow the mathematics of the Landau levels have not been studied that much until the last 10 years, and there's still a lot to do. So the Landau levels raising operator does something interesting to an analytic function. So we will call the function analytic if the function depends only on z. Okay? So if we have like a function depending on z and z bar, this will not be an analytic function. And we are going to consider functions that have coefficients which are analytic functions, and they are polynomials in z bar. Okay? So these functions are not analytic anymore. They are called polyanalytic functions. And if, to give an example, if we apply the raising Landau levels operator to the function z, if we apply that operator, we are going to obtain 1 minus z bar times z, which is modulus of z square. Okay, and here we see already something that is a fundamental difference between analytic and non-analytic functions. So analytic function cannot vanish on an accumulation set point without vanishing.
Sorry, you mean nabla z plus, right? Or is this a Laplacian you wanted to write?
No, it's that operator.
Yeah, so it's nabla. You denoted it by nabla for the.
Oh, this is.
Thanks.
Okay. Okay. So that function that function vanishes on the. Okay, this says zeros are the unit circle. Okay, so this is already a fundamental difference. So this is, I really want to explain the action of these operators. So this is the action of, okay, on Zn, it's not important. So this operator is going to raise the degree of Zm bar. So we can see the Landau level where we are by the coefficient of this polynomial. Okay, so the Landau levels lowering operator does exactly the opposite. It takes the degree of z bar to the n to the degree of c bar to the m minus 1. And the Landau levels, properly set, are the eigenvalues of this operator, which is the Landau operator. Okay, so the spectrum is pure and constituted by the natural numbers. And for each of these natural numbers, which are the Landau levels, those that create the plateaus in the integer quantum Hall effect, we have an eigenspace with reproducing kernel given by a Laguerre function times the Fock reproducing kernel. Okay, if you take n equals 0 here, you will get just the reproducing kernel of the Fock space. So the Fock space of analytic functions is the lowest Landau level. So let's start with a Gaussian analytic function. Okay, it depends only on z, so it's an entire function. We want to look at the critical points. So we could look at the zeros of the derivative of that function. But if we do that, since the function is analytic, we will only get saddle points. So we are going to look instead to the critical points of the spectrogram of white noise, which can be written in terms of a Gaussian analytic function this way. So to do this, we take the gradient of the log spectrogram, and we get here a derivative in z, a derivative in z bar, and since the function is analytic, it only depends on z, so this derivative is going to be 0. And what we get here, if we factor f0, is going to be the raising operator of the Landau levels. So we can define the critical points as the zeros of the Gaussian entire function raised to the first Landau level. And I will use some notations to simplify the formulas. So the 1-point intensity is divided by pi. This is notation I'm going to use to point process. So the first intensity of the point process, and here the n of the Landau level, because I'm going to show some intensities of zeros, of maxima, of critical points. So this will appear here first. And then here, the Landau level. Okay, so for n equals 0, this is going to be entire functions. So the zeros of Gaussian entire functions, the 1-point intensity is constant equal to 1. Okay? So this is important to fix notations. I'm not going back to this. Now the first result will use this notation. So the critical points of the Gaussian entire function in the 0 Landau level as a density 5/3. The density of the local maxima is 1/3, and the density of saddle points is 4/3. So an outline of the proof idea. At the critical point, we have a relation between the determinant of the Hessian of this log spectrogram and the Jacobian. If the Jacobian is positive, then this is going to be a maximum, because with properties of entire functions, we can prove that the minima are zeros. And this is important because we can only do this for entire functions, for f0. If the Jacobian is negative, then the point is a saddle point. So this allows to introduce these conditions on the Cock-Rice formulas, and we obtain 1/3 for the local maxima, 4/3 for the saddles, and 1 plus 4, we obtain 5/3 for the critical points. So what is interesting here is that this matches what was predicted by Patrick Flandrin in basis of experiments and heuristics, that the zeros and the local maxima, they are distributed according a network like a double honeycomb. So you have these hexagons around the local maxima, which are these big points, and you have these smaller hexagons around the zeros. And the area of these big hexagons is 3 times the area of the small hexagons. So this gives this 1/3 relation. So this is, of course, this is conjecture, and these numbers offer some support to the conjecture that the zeros will follow some random perturbation of that hexagonal lattice, and the same thing for the local maxima. There is a paper by Sodin and Cyrilson where there is something about the zeros of the Gaussian entire function and the hexagonal lattice. I will leave the reference. Maybe someone who knows more about Gaussian entire functions can look at it. So let's recall what we already know about higher Landau levels. We have a Gaussian entire function, and we already seen a Gaussian function in first Landau level, which is this operator, which was giving the critical points acting on that one. So this operator acting on z to the k is going to give this. So there's the z bar marking the first Landau level. The zeros, we already know that the intensity of the zeros in the first Landau level, it's going to be the intensity of the critical points in the zero Landau level, which is 5/3. And we know that there is a relation with the spectrogram of white noise with H1, the first Hermite window. Okay? So we know something else. We have an interlacing property of local maxima, if we can call it like this. So the maxima of the spectrogram with the Gaussian separates the maxima of the spectrogram with the first Hermite window. I mean, this is obvious because the maxima of this are critical points. And critical points are 0 of this. If they are 0 of this, they cannot be maxima. So this is, we have interlacing deterministic property. So in higher Landau levels, we are going to iterate this construction. We start with the Gaussian entire function again. We do the same things, but we apply the operator, the raising operator of the Landau levels, iterated n times with this factor here. We are going to obtain a sequence of orthogonal Gaussian functions with correlation kernels given exactly by the reproducing kernels of the Landau levels. So this Gaussian polyanalytic functions can be written in terms of Hermite polynomials, complex Hermite polynomials in Z and Z bar. The formula may look a bit complicated in terms of Laguerre function, but there's something to notice here. This part is radial, and here, so we have here monomials, okay? And this is going to keep an important property of the monomials of analytic functions, which is the orthogonality in concentric disks, okay? Because we can separate the radial part from the monomials. And this is useful to prove some things. So let's look at zeros in higher Landau levels. This is probably the third time that this formula appears, but it's always good to repeat things like this. So the raising of the zero Landau level Gaussian function is the first Landau level Gaussian function, and the intensity of zeros is equal to the critical of the zero level, so it's 5/3. for general N, there is a relation with the spectrogram of white noise, with short-time Fourier transform of white noise with the general Hermite window. And using this relation from this theory of Gaussian Weil-Heisenberg functions by Jaime, Colliander, and Romero, there is a general expression for the density of zeros. And it's going to increase with n. We have obtained, this is work with Tomiyuki Shirai, the density of the critical points in the n Landau level, and it has fabulous growth. And also the saddle points and extrema. How this is done, I'm going to make the basic computation here. We look at the critical points equation, exactly the way that we did in the first Landau level. And we have dz and we have dz bar here. But in the previous computation, this dz bar was 0. Now it's 0 no more, because the function is not analytic. So we are going to obtain from this and this the raising operator of the Landau levels. And we are going to obtain from this the lowering operator of the Landau levels. And the result is this equation for the critical points. Now, these operators, when acting on short-time Fourier transform, they have some sort of intertwining property with the degree of the Hermite function. So this can be written as the short-time Fourier transform with the Hermite window n minus 1 and Hermite window n plus 1. So this is also a Gaussian Weil-Heisenberg function. And we can use the theory of zeros, the general theory of Jaime, Romero, and Colliander. And the charged zeros are going to give this too. So the zeros were computed and we obtained this. With the charged zeros, we obtain this. So the saddle plus extrema, this is equal to 1, or the saddle minus extrema, saddle minus extrema. Right. So, okay, so let's go to the story of the multi-taper estimator. We have an average of Hermite spectrograms of a single realization of a signal. This was suggested as a multi-taper spectral estimation for the Wigner-Wille spectrum. In the case of white noise, we already know that this is going to be 1, but there is no proof. So this is reminiscent of Pythagoras' theorem. Like we have a sum of squares equal to 1. So maybe something similar to Pythagoras is happening here. So let's see how Pythagoras' theorem works for sines of cosines. We have always sine plus cosine complementing each other, so the energy allocation of sine square complements the energy allocation of cosine square. Maxima and zeros are interlaced. So between two maxima of sine, we have a maxima of cosine. Between two zeros of sine, we have a zero of cosine. So this is a perfect model of interrelation property and of complement of this energy allocation. So this is a bit the intuition why all these squares sum to 0. But so we can ask this natural question. Do maxima and zeros of the spectrograms of white noise with different windows tend to interlace? So there are some experimental work. So these are spectrograms. The orange, I think you can see orange here and here are high energy. So like this and this are supposed to be local maxima. So there's a local maxima here, and in the next one, the local maxima disappears. So there's another local maxima here, and it disappears in the next one. So these things here are probably zeros, these things, and they are also disappear here. This is not so easy to see, but the idea is that where we have high energy points here, we have low energy points here. Where we have low energy points here, we do have high energy points here. So the spectrograms seem to complement energy of each other. So this was also studied by Patrick Fondrin, and he looked at maxima. So he allowed me to use this picture. So this is the Hermite zero, the local maxima. And these are the local maxima of the Hermite zero spectrogram superimposed with the first Hermite spectrogram. So you can see that they are in different places. So that there seems to be here repulsion. Okay, and the interesting thing is that this keeps on happening when we add one more. So when we add 4, we already have almost a cover of the time frequency plane. So this suggests that maxima interlace. Now the problem is that we really have a problem with maxima in higher Landau levels, because the functions are not analytic and we cannot assure that local minima are zeros. So this is really the problem with maxima. So at least with the techniques we've been using, this seems hopeless to prove. But this is something we can do, and we do a lot in time frequency analysis of spectrograms. We have something about maxima, and there is some correspondence about zeros. That is the maxima zeros duality. So we can also ask if zeros interlace. We already seen in the previous picture some evidence of that, which means that there may be some repulsion between zeros of different levels. So this is our main result. Is about this interlacing property. So this means that the orthogonality of n and n plus k is strong, so that it means that the orthogonality is not due to cancellations. It's really a strong form of orthogonality, like caused by complementary allocation of energy in the time frequency plane. So we keep on asking the question. Okay, so there is repulsion, so this means all the same thing, like energy placed in complementary regions, repulsion, and interlacing properties. That's the idea here, because what we will have is not a real interlacing property. We will have some tendency to interlace, which can be measured by repulsion. So to measure the repulsion, we look at the correlation between zeros of the function, Gaussian analytic function in the n Landau level, with zeros of the Gaussian analytic function in the n plus k Landau level. And we will normalize this with the 1-point intensity. So it's the correlation between the zeros of n and n plus k over the 1-point intensity of zeros of n and the 1-point intensity of zeros of n plus k. And this is the pair correlation function. So if this is less than 1, we have repulsion. If this is equal to 1, we have neutrality, so it's like a Poisson process. And if this is bigger than 1, we have attraction, like a permanent toll process. So we did this computation, and the result is, at the first sight, maybe a bit surprising. We have the...
Sorry, how do you define the cross,
Right.
the cross row 2 between 2-point processes? I guess you just take the test function of one and the other, and you sum and take the expectation?
Right.
Alright.
Right. I didn't put that here. Yes. So the result we got is that between the level n and n plus 1, there is indeed attraction. And for the other levels, there is no interaction. I mean, the points don't feel each other. So there is indeed repulsion between zeros of consecutive windowed spectrograms. The zeros of consecutive spectrograms tend to interlace, and for k bigger than 1, the zeros of this spectrogram don't fill the zeros of that short-time Fourier transform. Okay, why this is happening, it's not completely clear. If this is like some physical intuition behind, saying that the Landau levels are far apart, so they don't interact with each other. So there is some physical ideas about the mixing and interaction between Landau levels. That is something that I think is not studied in mathematics. But in terms of the spectrogram, this may have a simple explanation. So the zeros of Hn and Hn plus 1, these are Hermite functions, so they are interlaced as orthogonal polynomials. Between two zeros of Hn plus 1, there is one zero of Hn. So it seems that this interlacing of the window somehow manifests in the white noise spectrogram and produces some interlacing in the zeros of the spectrogram. This is the what I believe that is happening here. So for the ideas of the proof, we simplified we use these formulas to simplify the vector. So we take this vector for the correlations, and we are able to compute the correlation matrices and get some simplifications by computing these Landau levels this way, because they will give different functions of the family. So for general Z and omega, the Cock-Rice formulas are intractable. This was something that was already appearing in Gunther's talk. This seems to be a pervasive thing when we are in non-analytic functions. It's really impossible to deal with the formulas, but some limiting cases, some asymptotics. What happens here is that when omega goes to 0, many entries of the correlation matrix vanish. So the last result is the long-term long-range correlations, that there is no surprise here. So the zeros don't fill each other when they are asymptotically far apart. Okay, this is what I was preparing to present. So the main references, so this is the book by Patrick Flandrin, where these questions are posed or suggested. I mean, this is really a source of research ideas for time frequency analysis and Gaussian entire functions. This is the preprint. I've been correcting it for some time. I think that this version already has few or no mistakes, so it's readable. And this was supposed to be out, but we have some new things, and it should be like in next month. So next month it should appear. This is the paper that was already mentioned here. So this paper by Feng studies the correlations between zeros and critical points. It's not the only paper studying correlations between zeros and critical points, but in this paper the critical points are defining using something that in differential geometry is called the Chern connection, which corresponds exactly to the raising operator of the Landau levels. This is the paper where I got the main ideas for the local maxima. It's a paper in string theory originally, so supersymmetric vacua, if I understood it, there are some things like black holes, something like that absorb energy. And critical points in compact Riemann surfaces, they represent supersymmetric vacua. This is done for all compact surfaces. It doesn't include this case of the Fock space, which is a universal case. It's a bit surprised because normally the dizziest case is computed first, but for some reason this was done in this very complicated case, but not on this more simple case. This is where there is something about asymptotic similarity of the zeros of Gaussian entire functions with something that looks like a perturbed hexagonal lattice. So there may be something here in the direction of this Flandrin honeycomb model for the zeros. Of course, for the local maxima, there's nothing for sure. So to prove that zeros and maxima follow that distribution predicted by Flandrin is an open problem, and it shouldn't be easier for the maxima because one needs to deal with a two-point intensity, but maybe it's possible to do some asymptotics. I don't know. So yeah, so this is a conference on determinantal point process. I'll leave some reference for determinantal point process on higher Landau levels. Let's start with this paper by Jaime Handelman. So actually most of the people here are in this conference. Then there was this paper by Shirai. This is probably the deepest paper on the topic. There is a universality property for the reproducing kernels of the Landau levels. So they have like this property that appears with the Dyson kernel and all these kernels in random matrix in the planar case. So this is the Weil-Heisenberg ensemble, which is defined using time frequency analysis, and in particular cases it gives the Landau levels. And the central limit theorem, and there is also a paper by Gauthier-Lambert. By the title you cannot really see it, but it also deals with higher Landau levels, and in particular it computes an estimate for the entanglement entropy here. So, thank you.
Thank you. Questions?
So, so you said there is an argument to say that for the critical point of F0 are the zeros of F1. That's right?
The critical points, it's not F0 because the critical points of F0 defined with the derivative. They are the saddle points. So the critical points of the modulus of F0 weighted by a Gaussian. So the critical points of the spectrogram.
Okay,
right. And then yes, so they are given by the zeros of the Gaussian function in the first Landau level.
More questions?
Shows you the slide where you have the local gradient to local.
The one in the higher Landau levels?
Yeah.
This one. Yeah, it's the point is that the function is not analytic, so you can yes, so it doesn't vanish, so you get this part for the critical points, and it's a sum of two Hermite functions in the window. But this follows from those results follow from your 1-point intensity and the charge at zeros. So you just cannot separate the extremal points into they can be minima. They are both minima and maxima.
Sorry, I have one. What do you mean by entanglement entropy? How is it?
Oh, okay. I can explain you more. I mean, I will have to really explain carefully.
What paper was it in? Was the last
I have myself a paper where I estimate the entanglement entropy of the Weil-Eisenberg ensemble, and I can show to you this. But they have here some. I mean, the definition is really technical
But it's something you can compute if I give you a point process.
A determinantal point. Okay, so it can be computed from the eigenvalues of the Toplitz's operator restricting the reproducing kernel to a region.
And it corresponds to a measure of disorder of my point process, or?
It yes. I mean, so this is the only concept of entanglement that can be defined with a single system. But originally, it comes from entanglement of two different systems. But you can, I mean, you extract some mathematical definition, and you can define the entanglement entropy of the determinantal point process. That's, I mean, this is my interpretation and the way I see and the way I work with it. I mean, Gautier does something a bit different there. He estimates the Renyi entropy of some. So in these cases it's a bit surprisingly bounded by the variance. So it's implied by hyperuniformity implies area law here.
All right. If no other question, let's thank the speaker again.